Welcome to the Deep Dive, the show engineered to cut through the noise and deliver powerful insights. Today, we're plunging into large language models, or LLMs. These things are, well, they're everywhere now, right?
They really are.
They're fundamentally reshaping AI from the chatbots you might bump into online, all the way to systems creating original content.
Yeah, it's a massive shift.
So our mission today is to give you a real deep understanding of these complex machines. We're going to distill the key knowledge, maybe some surprising facts, from a really comprehensive guide on essential LLM concepts.
And what's truly amazing, I think, is just the sheer speed of it all, how fast LLMs are evolving.
Right.
So this deep dive, it's really about equipping you not just with the basics, but digging into how they work, why certain designs were breakthroughs, and, what it all means practically as they get woven more and more into our world.
Okay, so let's open the hood then. We hear LLM constantly. But for someone who follows this space, what really defines these models? What makes that large part so critical compared to older AI?
Well, at their heart, LLMs are AI systems trained on just absolutely colossal data sets of text, massive amounts.
Okay.
And what defines them, the largeness factor, is really about scale. We're talking models with billions, sometimes even trillions of parameters.
Billions, wow.
Yeah, and it's that scale that lets them develop this incredible knack for understanding context, generating language that feels, well, human-like.
Yeah.
They handle tasks like translation, summarization, complex Q&A with the kind of fluency we just didn't see before.
So it's this sheer volume that lets them pick up on subtleties.
Exactly. Subtle linguistic patterns that smaller models just couldn't grasp.
That makes sense.
Yeah.
Okay, so before an LLM can even start understanding at that scale, how does it actually read? How does it take our words and turn them into something a machine can crunch? This must be tokenization, right?
Tokenization, yeah, that's the absolutely critical first step. It's basically breaking down raw text into smaller chunks, tokens.
Chunks, okay.
And these aren't always whole words. They can be subwords, like parts of words, or even individual characters.
Subwords, like artificial, becoming art, ific, al.
Precisely. That kind of subword approach, like BPE or word piece, is super important. It lets the LLM handle tons of languages, deal with rare words, even words it's never seen before.
Ah, so it doesn't just choke on a new word.
Right. It breaks it down. And it helps optimize the vocabulary size, making things more efficient. They don't work with raw text. They need these numerical representations of tokens.
Which brings us to embeddings. We have tokens. Now, how do these numerical representations give the model a sense of meaning? What are embeddings?
Embeddings are essentially dense numerical vectors. Think of them like coordinates in a high-dimensional space.
Coordinates?
Yeah, like a unique multi-dimensional fingerprint for each token. And this isn't just about identifying the token. It's about capturing its meaning, its relationships to other tokens.
So words with similar meanings are closer together in this space.
Exactly. King and queen would be relatively close. King and, say, cabbage would be far apart. It gives the model a mathematical sense of semantics.
How do they get these coordinates? Are they pre-programmed?
They're often initialized, sometimes randomly, sometimes using pre-trained embeddings like glove or word2vec, which already capture some general semantic relationships.
Okay.
But then, crucially, they get refined during the LLM's training. The model learns better, more context-specific embeddings based on the data it sees.
Got it. Okay, this is where things get really interesting for me. The transformer architecture. Older models struggled with long sentences, context. How do transformers process info so well and handle huge amounts of text? What makes them such a leap?
Transformers were a monumental leap, absolutely. A fundamental shift from older C2-sec models like RNNs or LSTMs.
Also.
The core innovation, the real magic bullet, is the self-attention mechanism.
Self-attention, okay.
Unlike RNNs that process words one by one, sequentially, transformers can look at all the tokens in a sequence simultaneously. This parallel processing is huge for scalability and speed.
So it sees the whole sentence at once, basically.
In a sense, yes. And second, self-attention is fantastic at capturing long-range dependencies. It can connect words or ideas that are far apart in the text, which was a major headache for older models.
Right, like connecting a pronoun back to a noun much earlier in a paragraph.
Exactly. And finally, since attention itself doesn't know about word order, transformers use something called positional encodings. These are added to the embeddings to give the model information about the position of each token in the sequence.
So it knows the dog chased the cat isn't the same as the cat chased the dog.
Precisely. Order matters, and positional encodings preserve that.
Let's dive a bit deeper into that attention idea. You said it lets the model focus. How does the attention mechanism actually figure out which words are important to which other words?
It's a great analogy, the focus one.
Oh,
Attention works by calculating weights. For each word, it computes how relevant all the other words in the sequence are to it.
how does it calculate that relevance?
It uses internal representations called queries, keys, and values derived from the token embeddings. Essentially, a word's query asks, "What am I looking for?" And it compares this to the keys of all other words. What information do you represent? High similarity means high relevance.
Okay, so in The Cat Chased the Mouse, when processing mouse, the attention mechanism would likely assign a high weight to chased.
Exactly. It figures out that chased is highly relevant to understanding the role of mouse in that sentence. It dynamically weighs the importance of different parts of the input for contextual understanding.
And building on that, what's multi-head attention? Is it just doing that same process multiple times?
Sort of, but it's more clever than just repetition. Multi-head attention runs the attention mechanism multiple times in parallel, but each time with different learned transformations of the queries, keys, and values.
Okay. What does that achieve?
It allows each head to focus on different kinds of relationships or different aspects of the input simultaneously. For instance, one head might focus on syntactic relationships, like subject-verb agreement, while another head might focus on broader semantic connections. It gives the model a richer, more multifaceted understanding of the text by looking at it from multiple perspectives at once.
That's powerful. So within this transformer, we often hear about encoders and decoders. What are their specific jobs? How do they fit together?
Right. In the original transformer architecture, designed for tasks like machine translation, you have both. The encoder's job is to read the input sequence, say the sentence in French, and build up a rich, contextualized representation of it. Think of it as understanding the source text deeply.
Okay, it encodes the meaning.
Exactly. Then the decoder takes that encoded representation from the encoder and, starting with a special start token, generates the output sequence, the sentence in English, one token at a time.
And it looks back at what it just generated.
Yes, it uses the encoder's output and the tokens it has already generated in the target language to predict the next most likely token. That's the autoregressive part.
So translation is a classic example. Encoder understands French. Decoder generates English based on that understanding.
Perfect example. Though some models, like BERT, are encoder only, and others, like GPT, are decoder only, depending on their primary task.
Got it. And just quickly on the math, you mentioned attention scores. How does the softmax function fit in, and what about the dot product in self-attention?
Okay, so the dot product is how the similarity between the query and key vectors is typically calculated. It's a simple, efficient way to measure how aligned two vectors are. Higher dot product means higher relevance.
So Q times K.
So Q dot K, yeah, often with a scaling factor involving the vector dimension. Now, these raw scores could be anything. The softmax function takes these raw scores and squashes them into a probability distribution.
Meaning they all add up to 1.
Exactly. So the weights assigned to different words become percentages, telling the model where to spend its attention. The most relevant words get the highest probability scores. It makes the attention focus sharp.
Right. Though you mentioned that dot product attention can get computationally expensive for very long texts.
It can, yeah. Its complexity grows quadratically with sequence length. That's spurred research into more efficient alternatives, like sparse attention mechanisms that don't compute all pairwise interactions.
Fascinating. Okay, so we have this powerful architecture, but how did these models actually learn language from all that raw text? What are the training strategies? Let's talk about masked language modeling, MLM.
MLM is a really clever and influential pre-training technique, famously used in BERT. You take a sentence and you randomly mask out or hide, say, 15% of the tokens.
Just replace them with a mask token.
Yep, or sometimes replace them with a random word or keep them the same. Then the model's job is simply to predict the original tokens that were masked, based only on the surrounding unmasked words.
Like a fill-in-the-blanks game.
Exactly, but on a massive scale. And crucially, because it uses context from both the left and the right of the mask, it forces the model to develop a deep bidirectional understanding of language.
Not just predicting the next word, but understanding context all around.
Right. That bidirectional context is key for tasks requiring nuanced understanding, like sentiment analysis or question answering.
And what about next sentence prediction, NSP? That often went alongside MLM, didn't it?
It did in the original BERT paper. For NSP, the model gets pairs of sentences, A and B, and has to predict whether sentence B is the actual sentence that followed sentence A in the original text, or just some random sentence from the corpus.
So learning about sentence relationships.
Precisely. It aimed to teach the model about coherence and relationships between sentences, which seemed useful for things like Q&A or natural language inference, though its actual benefit has been debated a bit since then.
Interesting. So these training goals lead to different model types. What's the core difference between how autoregressive models like GPT learn versus masked models like BERT?
It boils down to their training objective and how they see the data. Autoregressive models like GPT are trained purely to predict the next token in a sequence given all the preceding tokens.
Always looking forward.
Always looking forward. They process text strictly left to right during generation. This makes them naturally excellent at generative tasks, writing text, completing prompts, creating stories. Masked models, like BERT, use that MLM objective we discussed. They learn by predicting masked tokens using the full bidirectional context, left and right. They see the whole sentence, including future words, during training, albeit with masks.
So they're better at understanding the whole picture.
Generally, yes. Their strength lies in tasks that require deep understanding of the entire input context, like text classification, named entity recognition, or extractive question answering. Their training shapes their specialty.
That makes perfect sense. Now, a huge challenge, these models learn so much, but how do you teach them new things, maybe update their knowledge, without them just forgetting everything they learned before, this catastrophic forgetting problem?
Ah, yes, catastrophic forgetting. It's a classic problem in neural networks. You train a model really well on task A, then you fine-tune it on task B, and suddenly it performs terribly on task A. It's like the new knowledge overwrites the old.
So how do you combat that?
Well, there are several strategies. Older methods involve things like rehearsal, where you mix data from the old tasks with the new tasks during fine-tuning, or elastic weight consolidation, EWC, which tries to identify and protect the weights in the network that were most important for the old tasks.
But these days, the big buzz is around PAFT, right?
Yeah.
Parameter-efficient fine-tuning.
Exactly. PEFT techniques have been a huge breakthrough, especially for giant LLMs. The core idea is don't retrain the entire massive model. Keep most of the original parameters frozen.
Frozen, so unchanged.
Unchanged.
Right.
And instead, you add a small number of new trainable parameters, or you adapt existing ones in a very specific low-dimensional way.
Like LoRa, low-rank adaptation.
LoRa is a prime example. It injects small, trainable rank decomposition matrices into the transformer layers. You only train these tiny matrices, not the billions of original weights.
And that avoids catastrophic forgetting.
Largely, yes, because the original knowledge stored in the frozen weights is preserved, and it's incredibly efficient computationally.
And then there's QLoRa. What does a Q add?
QLoRa takes LoRa a step further by adding quantization. It loads the big frozen base model using very low precision, like 4-bit numbers, which drastically reduces memory usage.
4-bit, wow.
Yeah, but it performs the LoRa adaptation calculation in a higher precision, like 16-bit, to maintain performance. The combination means you need vastly less GPU memory.
Which is why people got excited about fine-tuning huge models on single GPUs.
That's exactly it. QLoRa made fine-tuning models with 60, 70 billion parameters feasible on consumer or prosumer hardware. A massive democratization of LLM customization.
Incredible efficiency. Speaking of efficiency, how do you shrink these giants down for devices like phones? That's model distillation, isn't it?
Yes, model distillation is the key technique there. You have your large, powerful teacher model, which is very accurate but too big to deploy on edge devices.
Okay.
Then you train a much smaller, more compact student model. The student learns not just to predict the correct answer, the hard labels, but also to mimic the output probabilities or internal representations of the teacher model.
So it learns the teacher's reasoning process in a way?
Kind of, yeah. It learns from the teacher's nuanced outputs, the soft labels. This helps the smaller student achieve much better performance than if it were just trained from scratch on its own.
And the result is a smaller model that fits on a phone but performs almost as well as a giant.
That's the goal, and it often works remarkably well. You get reduced memory footprint, lower latency, less computational costs essential for on-device AI.
Okay, so we had these trained, maybe even distilled models. How do we actually interact with them effectively? How do we guide them to give us the specific kind of output we need? This seems like prompt engineering.
Prompt engineering has become absolutely vital. It's the art and science of crafting the input, the prompt that you give to the LLM to get the best possible response for your specific task.
It's more than just asking a question.
Oh, much more. The way you phrase the prompt, the instructions you give, the examples you might include, that's few-shot prompting. It all dramatically affects the quality and relevance of the output.
Can you give an example?
Sure. Instead of just saying, write about climate change, a better prompt might be, write a 500-word blog post explaining the main causes of climate change for a general audience. Focus on clarity and avoid overly technical jargon. Include a call to action for individual responsibility.
Much more specific.
Exactly. Good prompting guides the model, leveraging its existing knowledge effectively, especially in zero-shot or few-shot scenarios where you aren't fine-tuning the model itself.
Makes sense. What about when the model encounters a word it literally never saw during training? How does it avoid just stopping or outputting garbage? Handling out-of-vocabulary words.
That's where the subword tokenization we talked about earlier really shines. Techniques like byte pair encoding, PEEPS-E, or sentence piece are designed precisely for this.
How do they help?
Instead of having a fixed vocabulary of whole words, they work with subword units. So, if the model encounters a new word like techno-optimism, it might break it down into known subwords like techno, optim, and ism.
So it can represent the new word using pieces it already knows.
Exactly. It can make an intelligent guess at the meaning based on the components and the context, rather than just treating it as an unknown UNK token. This makes the model much more robust to evolving language and specialized domains.
Very clever. Now, when the LLM is generating text, how do we control the output style? Sometimes you want factual, precise text, other times maybe more creative and diverse. What are the knobs we can turn, like temperature?
Temperature is a key one. It controls the randomness of the output. Technically, it adjusts the probabilities from the final softmax layer before sampling.
So low temperature means?
Low temperature, like 0.2 or 0.3, makes the model more deterministic, more confident. It will tend to pick the single most likely next word at each step. Good for factual answers, summarization things where you want predictability.
And high temperature.
High temperature, like 1.0 or 1.5, increases randomness. It makes less likely words more probable, leading to more diverse, surprising, sometimes creative, but also potentially less coherent output.
Is there a sweet spot?
Often something around 0.7 or 0.8 is used as a balance between coherence and creativity, but it really depends on the specific task.
Okay, what about beam search? How is that different from just picking the next word?
Beam search is a decoding algorithm that explores multiple possibilities, instead of just greedily picking the single best next word at each step.
Which might lead you down a bad path overall.
Exactly. Beam search keeps track of the k most probable sequences, or beams, at each step. For example, if k5, it maintains the 5 best sentence fragments generated so far and expands each of them.
So it explores more options.
Right. It looks ahead a bit more, often leading to outputs that are more fluent and globally optimal, especially for tasks like translation, where the whole sentence structure matters. It's less random than temperature sampling, though.
And top sampling, how do they fit in?
There are different ways to sample probabilistically, offering alternatives to pure temperature scaling. Top K sampling means you only consider the K most likely next words, and then you sample from just that set, usually adjusted by temperature.
So if K10, you ignore everything except the top 10 candidates.
Yep. It prevents really low probability, weird words from being chosen, giving you some control over the randomness.
And top or nucleus sampling.
Top is quite clever. Instead of picking a fixed number k, you pick the smallest set of words whose cumulative probability adds up to at least p.
Cumulative probability.
Yeah, so if p is 0.9, you look at the most likely word, then the next most likely, and so on, adding their probabilities until you cross the 90% threshold.
Right.
Then you sample only from that set of words.
So the number of words you consider can change.
Exactly. If the model is very confident about the next word, that set might be very small, maybe just one word. If it's uncertain, the set might be larger. It adapts to the context, often giving a good balance between coherence and diversity.
That's a really sophisticated toolkit for generation. But beyond just generating fluent text, how do we push LLMs towards better factual accuracy and maybe more complex reasoning? What are Ogg and Kati doing?
Right, those are two major techniques tackling those issues. Retrieval augmented generation, RG, is primarily focused on factual accuracy and grounding responses in real-world, up-to-date knowledge.
How does RQ work?
It combines a retriever component with a generator LLM. First, when you ask a question, the retriever searches an external knowledge base, like a collection of documents or even the web, to find relevant information snippets.
Okay, it finds relevant facts.
Then, these retrieved snippets are fed into the LLM along with the original prompt. The generator then uses this extra context to formulate its answer.
So it's not relying solely on its internal, potentially outdated or inaccurate training data.
Precisely. It grounds the response in external evidence, which drastically reduces hallucinations, making stuff up, and allows it to answer questions about recent events or highly specific topics.
Makes sense in chain of thought, COTI prompting. What's that about?
COTI is aimed at improving complex reasoning, especially for multi-step problems like math word problems or logical puzzles.
How does it prompt the model differently?
Instead of just asking for the final answer, a COTI prompt encourages the LLM to think step by step, or provides examples where the reasoning process is explicitly laid out before the final answer.
She asks it to show its work, basically.
Exactly. Like, question. Roger has 5 tennis balls. He buys 2 cans of tennis balls. Each can has 3 balls. How many does he have now? Answer. Roger started with 5 balls. 2 cans of 3 balls is 2, 3, 4, or 6 balls. So he has 5 plus 6 equal 11 balls. Final answer, 11.
Ah, breaking it down.
Yes. Forcing the model to articulate the intermediate reasoning steps seems to unlock its ability to perform more complex multi-step tasks accurately. And as a bonus, it makes the reasoning more interpretable for us.
Very cool. Shifting to the cutting edge now. We saw GPT-4 arrive after GPT-3. What were the really big steps forward there? And how are models like Google's Gemini pushing things even further, especially with multimodality?
GPT-4 was a significant jump from GPT-3. One huge difference was multimodal input. GPT-4 could understand images, not just text. You could feed it a picture and ask questions about it.
That's a big change.
Huge. It also had a much, much larger context window. GPT-3 was around 4,000 tokens, while GPT-4 models handle up to 32,000 or even 128,000 tokens in some versions. That means much longer conversations, analyzing larger documents.
Wow, remembering way more context.
Exactly. And generally, it just showed enhanced accuracy and reasoning capabilities, likely due to better training data, architectural tweaks, and much more extensive fine-tuning and alignment.
And Gemini, how is it advancing multimodal AI?
Gemini was designed from the ground up to be natively multimodal. It wasn't just adding image processing onto a text model. The goal was a more unified architecture for seamless reasoning across text, images, audio, even video.
So deeper integration.
Deeper integration, yes. They also highlighted things like advanced attention mechanisms optimized for cross-modal understanding and potentially greater data efficiency through sophisticated training techniques, aiming for scalability and stability in complex multimodal tasks.
Fascinating. Now, scaling these models, getting into the hundreds of billions or trillions of parameters, seems incredibly challenging computationally. How are organizations making that work? You hear about mixture of experts, MOE.
MOE is a really important architectural innovation for building truly enormous models somewhat efficiently. The core idea is simple but powerful. Instead of having one massive, dense network where all parameters are used for every input.
Which sounds expensive.
Extremely. In a MOE model, you have multiple smaller expert networks, each potentially specialized, and then you have a lightweight gating network.
What does the gating network do?
For each incoming token or input, the gating network decides which one or few of the expert networks are best suited to process it. It dynamically routes the computation to only those selected experts.
So you're not activating the whole giant model every time.
Exactly. Maybe only 10% or 15% of the total parameters are active for any given input. This dramatically reduces the computational cost, FLOPs, during inference, even though the total number of parameters might be huge.
So you get the benefit of massive parameter count for knowledge storage, but the compute cost of a much smaller model.
That's the promise, yes. It allows scaling to trillions of parameters while keeping inference manageable. Models like Mixtral from Mistral AI are prominent examples using this approach.
It's incredible technology. But let's be real, deploying these things isn't always smooth sailing. LLMs face some pretty significant challenges in the real world, right?
Absolutely. Despite all the progress, there are major hurdles. First, as we just discussed, they remain incredibly resource-intensive. Training and even running inference at scale requires massive compute power, energy, and cost.
Okay, the cost factor. What else?
Bias is a huge one. These models learn from internet-scale data, which is full of human biases, societal, historical, you name it. There's a constant risk they'll absorb and perpetuate, even amplify, these biases in their outputs.
Leading to unfair or harmful results.
Potentially, yes. Then there's interpretability, or the lack thereof. These models are so complex, it's often incredibly difficult to understand why they produced a specific output. They're often called black boxes.
Which makes debugging or trusting them hard.
Very hard. And finally, privacy is a major concern. They're often trained on vast data sets that might contain private information, and interacting with them involves sending user data, raising security and compliance questions.
So how do developers try to fix biased or just plain wrong outputs when they crop up?
It's an ongoing effort. Strategies include carefully curating and cleaning training data, trying to identify and filter biased content. Also, developing better alignment techniques during fine-tuning, using methods like reinforcement learning from human feedback, RLHF, to steer the model towards safer and more helpful responses. Analyzing patterns in bad outputs to diagnose the root cause, and sometimes targeted fine-tuning on specific failure cases. It's a multi-pronged challenge.
What an incredible journey we've taken today, really getting into the weeds of large language models. We went from the basics, how they even read text with tokenization and embeddings, to the core engine, that revolutionary transformer architecture, self-attention, multi-head attention.
Yeah, the real enablers.
We explored how they learn through masked language modeling, the differences between autoregressive and masked approaches, and how we fight catastrophic forgetting with things like PFD and the amazing efficiency of QLoRa.
And how to control them. Prompt engineering, temperature, RGG, chain of thought.
Exactly. And even touched on the giants like GPT-4, Gemini, and the efficiency of mixture of experts. I think understanding these principles really gives you the tools to make sense of this rapidly changing AI landscape.
I agree. And, knowledge like this is most valuable when you can actually apply it, or at least use it to think critically. Hopefully this encourages everyone listening to consider both the amazing power and the real limitations of these models.
Absolutely. A balanced view is key. So thinking about everything we've covered, the speed of progress, the remaining challenges like bias and cost, here's something to mull over. As these LLMs get even more capable and woven deeper into our jobs, our communication, our lives, what entirely new ethical dilemmas or societal shifts might we need to grapple with next?
That's a big question.
Definitely something to think about. We'll leave you with that until our next deep dive.